The following content has been provided by RWTH Aachen University.
Happy New Year, everybody, and welcome back to DIS1. The last class was a bit of a special event where we had a Christmas lecture sharing some things that I hadn't talked before here at any classes. And so because of that, we'll just take a little bit more time for the review. So it's the January moment of truth. Who looked at the video recording of the last class? Okay, that's a slim half, I would say. All right, we'll go over this. You'll have to watch this and make sure that you're comfortable with the material, because the evaluations that I didn't talk about live last time, it's not because they're not important. It's just because the material was recorded, and there wasn't anything that I wanted to change this year in this one. So I figured it's a good one to watch via video instead. So please do go over this, and I'll give you a quick whirlwind tour here now, but that's not going to be enough to really understand all this. So go back to the slides and the recording from last time. What the evaluation class was about was when, why, and where we evaluate. That was sort of the preliminary part, the opening part of this class. When basically referred to the fact, when do you do evaluations? Some folks did watch the video, so want to take a stab at that? Yeah?
It's happening in the analyze phase, but not just once. It should be just, we should go through it in every steps of software development.
That's right. So it's basically happening throughout the DIA cycles, iterations. Right? Every time you do get to the analyze phase, as you say, that's where you can apply some of these evaluation techniques. And which one you use will depend on which stage you're at, what your situation is, how easy it is to get to access to users and things like that. What are your goals when you evaluate? Like, what are you trying to get out of the evaluation? Does anybody remember what the why part of evaluation was going to tell you? Like, what is going to be the result of that? Yeah.
I would say that to see, well, first, like, feel the features of the system make sense in a way that they help the users actually solve the task.
Do you have a match of features supporting the tasks? Absolutely. Anything beyond that?
I guess just to find out if users actually understand how you implement the features. And like what problems.
Right. And also, one thing that we often ignore is gauging the effect on users that it has. Like, are they delighted by the idea that how the system is going to work for them, or are they like, this is weird, I guess I can use it, but something is off. And of course, to discover very specific issues, right? To see, okay, this one function or task I hadn't understood correctly, I'm supporting this wrong, right? So then, where does evaluation take place? Anybody from the having watched the video crew? There's two major sort of areas in which you can do evaluation. Yeah.
Whether in the usability lab or in the field.
Right. So you could do this in the lab with the users coming to you, basically. Has, of course, the advantage of being a very controlled setting, has, of course, the disadvantage of being a very controlled setting, right? So you can exactly set up what kind of things people are seeing, what tasks they're doing, if there are any interruptions or not. You can design all this in a controlled lab setting. But it also means it's not going to be as realistic as going out into the field, like visiting the user's workplace, for example, if you're developing a system for the workplace, or visiting users in their home if you're designing technology for the home, whatever it is. So the situation in the lab is a little bit less natural, but on the positive side, you can make sure these disruptions are controlled. Maybe there are none at all, or maybe you specifically design for certain interruptions, like having a phone call come in or something. And of course, you have all the equipment at your lab too, right? To do recordings of that person, to do screen capture, to do whatnot, audio, video recordings, etc. And in the field, you get a more natural behavior of people because they're in their environment that they're comfortable with, in which they normally are. So it makes them feel more comfortable and competent in doing their task. It's often also the only option, really, if you do a long-term study, right? If you ask people to use something for a long time, you can't expect them to sort of like move in and live at your lab. The naturalness of the field environment, however, is sometimes overestimated, because even if I'm in the field, if I'm using something and somebody is kind of watching me use it, I will still feel a little bit queasy about it, right? It will still not be perfect. It will still feel like a bit of a test situation. Okay, so then comes the big question: evaluation techniques. Anybody who watched this remember what kind of, this is a tree that we're talking about, like, of evaluation techniques. So what's the first division of that tree? Anybody recall this? Yeah? With or without users, exactly, right? So do I have users available or not? And there can be a whole bunch of reasons why you might not be able to get to users. Maybe you're designing something for the International Space Station, and it's kind of a long trip up there, right? And all your potential users are maybe up there right now. So, or maybe it's just that you're developing something, but you really don't want to show anybody yet, and you need to stay away from doing user tests. There's a bunch of different reasons. Sometimes cost reasons are also coming in, or time reasons. It always takes time to recruit users, a representative bunch of people that actually, not just your best friends as users, and then, designing a, I don't know, support system for the elderly, and then you test it with your fellow dorm, buddies in your student dorm, kind of a mismatch. So sometimes there is reasons for not testing with users, but that's the big division. Okay, and so anybody recall test options without users? Those that saw these. You can start with one. It's easy, right? So you can get yourself the whole list to pick from. Go ahead.
Yeah, so I remember one where, I'm just going to pick the easy one, which is literature review. Literature
review, exactly. Whole point being, before you do go in and run a long study about whether people are faster with pie menus, circular ones, or linear menus, maybe look up if somebody already did that study with a setting that is relatable to your own setting, so similar demographics, similar context. And if they have, then you don't need to run the study, right? As the joke goes, an afternoon, or let's put it that way, it's like a whole week in the lab can save you a whole afternoon in the library. Meaning that in reality, of course, short time in the library, these days that means going into the ASIM digital library and stuff like that, can save you a lot of work in the lab. And that's a big one, right? Literature review also comes up big time when we do all of our HSI research. So often that people come up with a crazy idea, like, I'm going to build this, I'm going to test it, and it's going to be awesome. And then they're done, and then they're like, oh, now I need to write this paper, and the paper needs this related work section. Oh, damn, now I need to read other papers that did similar stuff. And then you find like, oh, somebody actually tried this 10 years ago and they were successful, so I kind of wasted my time, right? So or they tried it and it wasn't successful, so I could have learned from that for my own work. So doing literature review early and continuing to do it is also important in research. But now we're talking about, industrial, customer-centered usability here, and there also literature research matters. And oftentimes in the industry world, that's kind of overlooked because they're like, yeah, those are these eggheads, in their ivory tower, and they're writing these weird papers, but that's not really relevant for our stuff. But there's a lot of things that big companies could fix in the products that just looked at a couple of the basic findings that are available in research. So literature review. Others? From the without users. Yep.
The next easiest one for me was
heuristic evaluation, yeah. Heuristic evaluation means you have a set of heuristics, which is a fancy word for guidelines. And you go through this list of guidelines with your system, and you look at it and see if those guidelines are met or being, strongly disobeyed. Let's put it that way. So that's one where you need, of course, that set of guidelines, and you need to step through your interface screen by screen, for example, or task by task, or whatever, and just do your best effort of seeing whether anything is coming up that looks like it breaks one of those guidelines. And the second part of today's class will actually be about a set of those guidelines. Yeah, go ahead.
For the heuristic evaluation, it feels like it makes sense more for redesigning stuff, like applying those rules to changing something, not just inventing from the beginning.
Yeah, yeah.
Because you also mentioned that if you have a blank piece of paper, you should start with the rules.
That's hard. Yeah, yeah. Yeah, thanks for bringing that up. The heuristic evaluation will have rules like, keep the interface as simple as possible. And that's great to know. And you can look at an interface, and once you see an interface, you can say, like, could I do this more simply, or is there some unnecessary complexity in this UI? But if you don't have anything, it doesn't help you a lot, right? It's good to have this in the back of your head. But yes, heuristic evaluation usually means that you have some kind of prototype and you evaluate it. But in a way, that's true with most of these things, right? Evaluation techniques only work in the analysis phase of your DIA cycle. And at that point, you have implemented something. You've built some kind of prototype. Even if it's just a story or a storyboard or a paper prototype, you've got something in your hand that you're going to apply those rules to. Right, and then we have another one without users. Mm-hmm.
I think we call it a cognitive walkthrough.
Cognitive walkthrough, yes.
Where like the designer kind of imagines a situation where like someone is using the system.
Yeah. Yeah.
Yeah, like from starting from the goal, like from the 7 stages of action, and how they would basically get from that goal to interact like with the system.
Yeah. So while heuristic evaluation is you can do with fairly little, you have the interface, you got your prototype, you got your list of rules, and you can already get started. Like, for example, if you take the Gestalt laws, right? We know they're universal, they always apply, and you can quickly pick out a couple of bugs in an interface by just thinking through, are all the Gestalt laws being obeyed, or are they used to good effect or to bad effect? Because you can't ignore a Gestalt law; it's still in place. You can't ignore gravity, right? But you can work with it or against it. And so, with the cognitive walkthrough, the idea is that you have much more available. Like, you've got a couple things. You've got your interface prototype, of course. Otherwise, you have nothing to test. In fact, you don't need to necessarily have the interface working, but you need a description or a definition of how it works, right? And then you have some kind of expert who knows how to run a cognitive walkthrough, who has the necessary HTI knowledge. And what they need to do is they need to mentally put themselves into the shoes of a user, right? They need to imagine being a user, which is hard, because it's hard to switch off your own expertise. But if you manage to do that, you need, or if you want to manage to do that, you also need a description of who the user is, right? What does the user know? Am I designing something for nurses at a hospital? And if so, what is their typical level of understanding of, this computer technology, this domain that we're doing this about? Like, how much do they know about, I don't know, anesthetics, stuff like this. So you need to have a model of who the user is that you're supposed to put yourself into. Right? Otherwise, that's kind of hard. And then you need a task description, right? If you want to do a cognitive walkthrough of an interface, you need to know what task the user is supposed to do with the UI. Otherwise, you're just going to look at it and not really know what to accomplish with it. So that's the cognitive walkthrough, and it has the advantage, like the others on this side of the list, that you don't need users to be around, right? But you need to know who those users, or what those users would be like. There's one more that you can do without users, which is also one that we're going to dive into a little bit more today. Anybody remember what that was? Yeah? It was something with models, right? Model-based evaluation, correct. It's actually the one that's possibly going to feel the most comfortable to you folks, because it is actually a fairly engineering-minded approach, where you actually can almost compute certain things of an interface and use existing models of how we understand, engineering models of how we know humans react to technology, apply them, and that gives us some kind of understanding of how good or bad UI is. And we're going to look at one of those today in more detail. Right. So that was the list without users. And then we had a list with users. So what were the techniques there that we talked about, that the video talked about last time? What can you do with users? The ones with users were kind of stacked on top of each other, right? Which one do you remember?
There was something like silent observation, where the user just uses your the implementation and
Yes.
you watch them, how they use it, and then look at what can I develop that the user thinks that's best.
Right. Silent observation, because I don't interfere with the user, right? I don't, as an experiment leader, so to say, as this researcher, I don't mess with the user. I don't tell them anything. Of course, you need to sort of get them settled into the experiment and tell them what this is generally what they're supposed to do, etc. But then you leave them alone with the UI and you just watch, right? This is hard. Especially if it's your own UI and you see people sort of slowly failing to use your UI with a task that you thought was super easy with this, it's like, like you're like scratching your fingernails. Talked to a friend at Microsoft who said that this was the best thing she ever did. Like, she put Microsoft engineers behind a glass wall and had them like these Venetian mirrors, right, the half see-through mirrors, and they had to watch people slowly fail at doing something simple with Word, and they were like, no, you need to press this button over there, but they couldn't talk to the user. So very healthy for a development team to do this. I think nobody who's involved in a software developed for users should go through the project without at least once watching an actual user physically in real life doing stuff with the software. You always learn something. I've been doing this for decades, and every time I did this, something surprised me about how people were doing stuff. Sometimes it's big things, sometimes it's little things, but you always learn something from just watching people use it. So highly recommended. But silent observation was kind of like the level 2 approach in working with users. What was the even simpler one? In silent observation, I need to give the user a task, right, that they do. If I don't give them a task and just give them a prototype and say like, what do you think this is? What would you do with this? What do you think these interface options mean? What's that called? Anybody recall? Yeah?
It's called model extraction. You basically try to find the conceptual model of the user, but it's only for like one step. For the first step, you don't find out how the user learns the system. You just find out that he knows that this is a button.
Yeah. So it gives you a sort of an immediate usability judgment, right? So remember the graph with the designer's model and then building the system image and that, creating the user's mental model, right? Where you communicate basically through the system image with the user indirectly as a designer. This is where you test whether that worked, right? So you give a UI to a user and you ask them, okay, so, maybe somebody who's never seen a desktop, right? So you give them a desktop and they, so what do you think this is? And they're like, oh, these little yellow things look like folders, and this looks like a trash can. And I think I guess I can open this folder. I don't know, maybe click on it. So you're going to discover what their conceptual understanding, their conceptual model is of the UI that you created. But you don't necessarily give them a task to work with. It's really more about the initial usability of a system. For simple things, this could be enough, right? If all you have is a weather app, then maybe that's all you need to do. Okay, so and then if this is not enough, so model extraction, silent observation, we want a little more. What else can we do? In silent observation, it's important that not only is the experimenter not talking, but the user is also not talking, right? They're just doing their thing. So like a normal person, not like a crazy person. You're not talking about what you're doing while you're doing it. Now we get to the next level, which is
think aloud.
Think aloud, yes.
Which is basically silent observation, but with speaking of the user. So,
exactly.
The user tells the observant what he thinks he is doing, what he is doing exactly, and how he understands.
Exactly, yeah. So there's like 2 or 3 things that you want so you're prodding the user to talk about what they're doing as they're doing it. And you ask them, to tell you what they are seeing. So it's a bit like the model extraction part. Like, so what do you think this is, right? So they're like, oh, okay, this looks like a button, right? And then you ask them when they do something to explain why they're doing it, right? So I guess, to open the file, I'm going to click this button. And then you ask them to also talk about their response, right? And when they see what happens, oh, window popped up. I didn't expect that. Or yeah, that's exactly what I wanted. So you ask them to constantly basically do a narrative track of their own, interaction with the system. So that's a bit like a crazy person, right? So constantly talking to the thin air around them, because they're not supposed to talk to you about it. It's more like really just voicing, basically creating a voice track to their own interaction. And because this can feel it, this is, by the way, the most frequent technique that you'll find in industry. Think aloud, most usability groups will know what that is, right? Think aloud, if you say that, a lot of people are like, yeah, that's what we do in our usability studies. But since it can feel a little weird talking to yourself, there is an option that builds on that, which is the last one that I think we mentioned under this list, yeah?
Just maybe, I guess, add another user. Like, they can also be more experienced in the first one, and then do like kind of trainer and trainee effects, but they could also just be in the same level, and they would just talk to each other and try to figure out the interface together.
Right. So you got 2 people, right, using the interface together. Could both be starters, like you say, starting off, or one of them could be a little bit more experienced and the other one hasn't never seen the interface. Then you get an interesting picture of 2 snapshots of like how people understand the interface from both the beginning and the advanced time. All right, and then we had, yeah, that's called constructive interaction. And the last one we had there was where you involve the user in the entire design process throughout, not just occasional user tests, but also have them really be part of the design team. So when you have design meetings and you make decisions about your next iteration of the prototype, you always have users as part of the team. And that's participatory interaction. Actually, a legally prescribed method in some parts of Scandinavia for like publicly used software in public institutions. Okay, so these were all qualitative, though. Right? Important distinction. What's the definition? What's the distinction between qualitative and quantitative methods? Yeah.
With quantitative methods, we usually get numbers,
Mm-hmm.
like how many people, how much time, or something like that.
Mm-hmm.
And then with the qualitative, we get why that happened.
Right. It's not that one is better than the other, especially from this engineering-minded crowd here in the room today, or in this entire building here. There's often a tendency to think that, yeah, quantitative, that's a real science, like a big S science, right, capital S science. And qualitative, yeah, da-di-da, weird, feelings and stuff. No, the quantitative stuff, I think you said it very well. The quantitative stuff gives you measurements, right? So people are taking 0.8 seconds longer using this kind of menu style than they do with this kind of menu style. That can be super useful if you need to decide which one to, deploy. you have no idea why that's going on, right? You just know one is faster than the other. If you want to know why, you need to ask that question. And the why question is not a number. Like they won't say, oh, that's because 42. Well, if they say that, then they're probably right. But if they say any other number, they're probably not right. So if you want to understand why something is happening, you need to actually talk to people and get insights, right, from them and watch them do it. Observe, for example, why they are taking longer. See the kinds of mistakes they might make with this slower interface, or talk to them and ask them why they're struggling with it, etc. So both things are equally valued, and often you need to do both to really understand what's going on. So for the quantitative methods, there's just one type of study. We mentioned that, and those are the controlled experiments. And that is the kind that is actually most similar to what we do in research, like what Marcel and all the other folks at our lab are doing a lot of the time is, in fact, quantitative research. Oh, actually, Marcel is doing a little more qualitative research recently, right? Yeah. So, but quantitative is something that we talk about a lot also in current topics in HCI. Great class to check out next semester, right? If you're interested in doing your thesis with us, that's a wonderful class to learn about the research methods in human-computer interaction, how you set up a study, how you do measurements, how you run the statistics around it, how you build experiments that actually tell you something interesting and exciting. Right, that's the tree, right? So we had evaluation techniques without users, literature review, cognitive walkthrough, heuristic evaluation, model-based evaluation. In model-based, we hinted at GOMS, which we're going to talk more about today. We also mentioned design patterns there, which is a way to have a rational, basically a mix between guidelines, very concrete style guides, and golden rules of general interface design. Watch the video to learn more about that. HCI design patterns happen to be a format that I introduced into the HCI community eons ago when I did my own PhD. And it caught on quite nicely now. There's a lot of books out there that use the format of an HCI design pattern to express knowledge and expertise about how to build interfaces. Evaluating with users, there's qualitative methods that we just talked about. I forgot to mention retrospective testing, right, which means after you did the study with the user did the task, you maybe have a recording of what you did, right, the video recording, and then you talk about the recording with them. That's sometimes a little easier than doing the think aloud while they're doing it, right? So then they can do the task without being disturbed by having to talk about it, and then they can comment on their own actions afterwards. But you got to do that right afterwards, otherwise people tend to forget the rationale why they did something. Yeah, and of course you can always run interviews, questionnaires, etc., to collect more information. All right, so those were the techniques. And the last thing we talked about in the evaluation class is how to deal with users. The idea is basically there not to waste their time, right? So if you invite people over to your lab or if you visit them in their workplace, you got to be super ready to run your study as effectively as you want, because they are donating their time more or less to your cause, right? So be aware of that. That's the one thing, don't waste the time. And the other one is there's always the sense of being scrutinized, right? If I come to you and I give you an interface, like, could you, do the following task with this interface for me, you'll feel like you're in a test situation, right? It's a little bit uncomfortable. So I need to communicate to you that, no, I'm not testing you, I'm testing the interface. And there's going to be problems, and that's exactly what you will help me find out about it, right? So make sure when you talk to testers that they understand that they're not being tested, that the system is being tested. Of course, you got to make sure that also otherwise they feel comfortable, that you guarantee privacy, for example, of results, right? You can't walk into a company and say, so we're going to introduce a new office system here for writing your letters, and so dear assistant or dear secretary, please use the system to write a letter, and we'll have your boss stand next to you and watch how you do that. And that's not going to be acceptable, right? Because they will be under extreme pressure. So anything people are doing usually stays between you and that individual person, right? And you got to make sure beforehand that you clarify to the user how the data that you're collecting is being used. And that's always been true in HCI for like 40 years, ever since people have been doing this, for a living. But of course, with the DSGVO in Germany and all the privacy laws, etc., really ramping up the raising the bar of how you need to apply to this. This has become much more of a red tape zone. So be very careful about this. When we run studies where we have, where we're doing things with users, participants, increasingly we're being asked to basically treat it almost like a medical experiment. Like, so you need to get approval from the internal ethics review board, et cetera, et cetera. You need to lay out exactly what kind of data you're collecting, how you process it, how you destroy it, et cetera. So this is a tricky business not to ignore. All right, so that's the brief story of evaluation techniques. Like I said, go back and watch this video in its entirety to understand these techniques a little bit better. But we're now going to take a quick look at GOMS. GOMS, I'm going to start explaining with a story. In 1995, Jakob Nielsen, who's a famous web design guru, had less than 24 hours to recommend if Sun should add three new home buttons, three new buttons to their homepage or not. Right? This, they asked him so what do you think? Should we do this or not? Jakob Nielsen is an interesting person. It's definitely worth checking out his alert box column. It used to be called, now I think it's called something else. But he's got interesting articles at his website. He's running a consultancy called the Nielsen Norman Group. And you can guess where the name Norman comes from, right? So he's doing this together with Don Norman. So these two folks have very interesting consulting advice, very business-oriented and very hands-on. So if somebody is asking you, okay, so this whole usability HCI thing, is that actually applicable to real products out there? Yes, they have lots of articles that are very down-to-earth, telling you what to do in a business setting for usability. Anyway, so he came back within 24 hours and he said, yep, each new button that is largely unused, that people only press very rarely, will cost visitors $500,000 per year. As a result, 2 of the 3 new buttons were taken back out of the design. Now, how did he do this? Was he did he have a Ouija board, or did he do some black magic? No, he actually used a mathematical model of interaction to calculate this cost. And since this question often comes up, how do you get to $500,000 per year? The thinking goes something like this. Times money. So looking at an interface with more buttons to pick one from will take a little longer than if those extra buttons that I hardly ever use aren't there. So putting more buttons on a page means the user is going to take longer to find the information they are interested in. You multiply that, you look at who is typically visiting the site, and of course, the Sun website is typically visited by fairly highly paid technical administrators and developers and stuff like this. So you know what their average income is per year. So you can calculate what every day, every hour, every second of their work time costs. And it's going to be a small number. But then you know how many visitors are coming to the site every year, right? So many visitors per year times their average income number per second, let's say, right? Small number. Will tell you, okay, if we look at our customer base as a whole, we are wasting their time and therefore their money at this magnitude if we change the interface in this way, if the interface becomes slower to use, right? Makes sense. And this is a trick I often see, right? The moment you can turn usability questions into dollar or euro questions, you've got your foot in the door in the company that you're consulting for or that you're working at. As long as you only say, but users are going to be so much happier. people are like, yeah, right, but you know, quarter results, blah, 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 money, capitalism. So the moment you can latch onto saying like, this is actually going to cost us money, or this is going to make us more money, then of course you're speaking the language of economy, and that will help making usability questions heard in corporations. So GOMS is interesting for that very practical reason. And that's what I like about it, because it is actually a very almost academic, almost mathematical method that is being used. GOMS stands for Goals, Operators, Methods, and Selection Rules, right? So those 4 letters are also the main components of this technique, which is a wonderful thing. Every time we do exams, everybody always remembers that, because the name encodes already the 4 basic parts that need to be in a GOMS model. It was published, get this, in a book, The Psychology of HCI, in 1983. So it's like ancient. They almost chiseled this into stone, right, at this time. And this is, of course, by Stu Card, Tom Moran, and Al Newell. And some of these names might ring a bell from this class. Look at the last names. CMN model, yes, bingo. Yeah, she hit the button first. Yeah, all right, that's right. So these are the folks that worked on the CMN model, right? And this is the book that I talked about back then. It's the same book that actually published the CMN model. All right, so, and the GOMS model is there to estimate execution and learning times of a system. And there's one thing that is really weird about the GOMS model, but that is also super important because it makes it extremely valuable. And that's the little word before a system is built. So you actually don't need a working implementation of a system and run a user study with it. You can actually only have a description of how the system works, and you can apply the GOMS method to it, and you can calculate execution time. So that's a little bit like black magic, right? I can tell you how long you're going to take to do the following task with this interface without actually building the interface. So this is an interesting model, and we're going to look at these 4 components now to understand what the idea behind GOMS is. The first one is goals. Goals describes users' end goals. This is a little bit, you could loosely relate this to what we talked about with the 7 stages of action, right? The high-level goal of a user. But here's one significant limitation of GOMS. Well, in practice, it's not that bad, because most of the things where you really want to optimize for execution times are things that people do a lot. Right? If I only use a system once every 3 months for 5 minutes, who cares about how long it takes? Right? It's not going to be that important. But if it's a system that gets used a lot, I get used to it, and I spend a lot of time with it, then it becomes important that it is fast, right? That it doesn't waste time. So the tasks that we can apply GOMS to need to be routine-ish tasks, things that we do a lot. Like not, I don't know, come up with a topic for your master's thesis or something like this, right? It has to be something fairly mundane, like copy editing a manuscript, meaning you've got a manuscript, it has, you gave it to me, I made all my weird marks on the side, and now you have to go back and sort of integrate the changes into your text, right? That's a typical task. We'll use this task actually as an example here in this class. Goals will lead to a hierarchy, sort of like a tree structure of sub-goals, right? And it doesn't necessarily mean that you execute all of these one after the other, but it could be that, let's say, copy editing a manuscript sometimes means I need to delete a word, sometimes I need to duplicate a sentence, sometimes I need to move some text to some other location. There's going to be different kinds of tasks that make up this larger task that I'm doing of, for example, copy editing a manuscript. And so Goals are at the top, so to say, of the GOMS tree, and then they fall into sub-goals, and we will get to the leaves of this tree next, which are the operators. Operators are the elementary user actions, physical user actions, like pressing a key or selecting something from a menu or dragging, dropping, reading a message on the screen, because while I'm not inputting anything, that also takes time, right, reading a message. Or any other, if it's a gesture controlled system, it's going to be a gesture. If it's a speech controlled system like your home assistant, then it's going to be it's going to be a voice command. And the trick is, what GOMS does, it breaks down these large tasks that you have ultimately down to all these operations, these basic operations. And for these basic operations, we can actually determine how long they will take on average. We've got a number. We've got a number in seconds. And the moment you inject seconds into the system at the very bottom, this can trickle up the tree. You can calculate average, statistically combined times for certain tasks, and boom, you've got money, right? You have execution times, which then tell you how much time people are spending and maybe wasting, at least what they're going to be costing when they do this task. In between are two more things that we need to understand. One is methods. So methods are like procedures in a programming language, or functions like in programming language. They can be just the subgoals I talked about earlier. Like, for example, delete a word could be a method. Why? Because deleting a word is not yet a single basic operator. Right? It's not a single click or something like that. I need to break it down further. Some methods can also already contain operators, so they can be like more procedure calls inside one of these procedures, more method calls if you want inside the method, but also there could be elementary operators inside the method. So you can see how all this is basically related to a tree diagram very strongly here. And the final thing is, as I said initially, copy editing a manuscript, it's not like I know exactly that people are first going to delete a word and then they're going to move a sentence, and so I don't know, right? But what I do know from maybe watching a couple of copy editing tasks is that maybe on average, I don't know, 30% of the time that somebody needs to copy edit a manuscript, 30% of the tasks are moving a sentence somewhere else. Let's say that I discovered that by watching people copy editing manuscripts a lot, or analyzing the movements that people are doing using a little tool. So methods are these procedures, but selection rules tell me when people do things, at what likelihood, and how they do it. So, for example, I might say deleting text only happens 30% of the time in the text. And now the question is, how do people delete text? Because you can delete text by going delete, 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 delete. And that's actually the preferred method if it's just 1, 2, or 3 characters, right? But if it's 500 characters, you're not going to be doing that, I hope, right? You're going to be using your mouse or some keyboard shortcut to do this instead. So there are different ways to do certain actions, and selection rules will tell the GOMS model which of these different methods people pick how much of the time, right? So in this case, I have them maybe 70% of the deletions happen by just pressing a bunch of keys, and 30% happen by selecting and then pressing delete, maybe something like that. So here are some examples. Again, copy editing a manuscript, like editing a text in your favorite word processor, right? One example could be that your goal, this is already a sub-goal within copy editing, right, within this task, to highlight some arbitrary text, right? So let's say I want to model one aspect of editing a text is highlighting, right, obviously. So how do I model this? I could say, well, one way to do this is to move the cursor to the beginning, click the mouse button, move the cursor to the end, shift-click the mouse button, and I've highlighted some text, right? you can do that. That actually still works today. This is taken from the author's original examples. So you can see like text editors haven't changed that much in 40 years. So this still works. But that's not the only way of doing it, right? I could also go in and have a different way of highlighting the text, because I could maybe say, oh, I'm going to highlight it by actually clicking and dragging the mouse to the end and letting go. And maybe that takes a different amount of time. Right? What you see here, though, is that this goal is actually falling apart immediately into basic operations. Right? There are no more sub-goals or methods being invoked. This is all basic operations. And we can see that there are times associated with each of these. Right? And these times are repetitive. Right? So moving the cursor to the beginning is a pointing operation. And this pointing operation seems to take 1.1 seconds. Moving it to the end takes exactly the same time, because on average, the operation to move the pointer to a point on screen takes 1.1 seconds. Now that's a big average, right? That says this is much more generic than Fitts' law. With Fitts' law, you know exactly what the distance is and how big the target is. Here we don't know any of that. We just say, if we go over all the distances possible on a typical computer screen and all the different sizes of things that people typically need to target, this is the average time this takes. Right? So it's of course, it's a simplification, but that's the only way you make this handle, you can handle this kind of complexity. Because we don't know what copy editing, what text people are actually copy editing, right? We have to make some assumptions on averages here. Yes?
So this is relatively context-free. How did Nielsen derive the statement that adding 2-3 buttons will cost like $500,000 more because adding buttons should not change these times?
No, it doesn't. It doesn't change the time. But what there were rules in operating a when you're using a website. One of the things that you're doing is, let's say what's the name of that law? I keep forgetting. Is it Hicks law? I think there's a law that says that the longer a menu is, the more options it contains, the longer it takes to actually find the right item. It's obvious, right? If you have a menu with 20 items, it takes longer than 5, and that tells you that you will have a longer dwelling time, longer reading time, basically, to read a message. Remember that one of the basic actions was also reading a message on the screen. So parsing a UI, looking for the thing that you want, is also part of these operations. Not in this, not what you see here, but in the web browsing task.
The UI, we have to also change the time.
Right. Well, you have to. What you typically do with GOMS is you have a particular class of user interfaces and applications. For example, anything you do on a computer in word processing, right? Whether you're writing an email or whether you're filling in a form or something like this. When you're using a computer and you're clicking around and you're hitting keys and stuff like this, then you have basic operators that will help you to estimate the time for this. But yeah, if the task is, for example, to browse through lots of hierarchical menus or through lists of buttons or menu options, then you might need a time for that as well. Yeah. But yeah, that's a good point. I might be able to dig out that story from Nielsen again, and if I do, then I'll send it around to you folks. So before we look more at GOMS in detail, I want to briefly lay out that there are a couple variants of it. The first variant is the one that I'm talking about here right now. So the original GOMS model from 1983 was the one that I just described with goals, operators, methods, and selection rules. Let you predict the time that an experienced worker needs to perform a task in a given interface design. Then there is the keystroke level model, KLM, which is a simplified version of GOMS. It basically works like GOMS, except I only look at a very specific task that I break down directly into a sequence of operators. So for example, when I say the task is to, I don't know, log into your laptop, right? Then it's pretty clear the moment your laptop is there, you need to press a button to wake it up maybe. And then maybe you need to move the pointer to the login window, click, and then you need to enter your username, hit enter, and then you need to maybe enter your password, something like this, right? So if I know exactly what that sequence is, I can break it down directly into operators. I don't have to make decisions about like, oh, with 50% likelihood they're going to use this technique or this technique. We have an immediate, basically linear sequence of operators at the bottom. And that's why it's called keystroke level model. It's at the level of keystrokes and mouse clicks and these kinds of very simple physical actions. Okay, so that's what KLM is referring to. You often see KLM referring to the GIE. That stands for graphical input device. It's basically a fancy name for the mouse. And what you can do with that is, if you have the keystroke level model, that you can actually rank the performance of different input designs by how long it takes to operate each interface to do the same task. Beyond the basic GOMS variant, there is KLM was also introduced by Cartmore and Newell as a simplified model for simple modeling tasks. And CPM was developed later. That stands for critical path method. And it discovered something interesting. It said, if let's say I am looking at a screen, I have to click at the beginning of a text and then shift click at the end, right? The original GOMS model said, I'm going to use the operation time to click at the beginning, plus the operation time to move my pointer to the end, plus the operation time to, shift click the end, plus the operation time to verify the result. And I'm adding all these. But we know from the CMN model actually that we can think of having these different processes in our brain that can somewhat overlap. So while your motor processor is doing the click on the starting letter of the text you're trying to select, your eyes will already be on their way to find the end point that you want to select, right? And so your different processors, if you want, your perceptual, motor, and cognitive processes, can overlap to a certain degree these tasks. And what people found applying the original GOMS model is that it was often overestimating the time it took to do things. It came up with numbers that were too long. And the reason people discovered was that it was not taking into account the fact that people were actually overlapping these tasks in their head. And CPM GOMS, the critical path method, did that. So it fine-tuned GOMS and said, under certain circumstances, if you're using different processes for these different tasks, you can actually sort of compress the overall time estimate a bit, because it won't take people that long because they are doing these things partially in overlapping times. So that's what the critical path method is about. And then there was the natural GOMS language model, which actually deviated from everything we've seen so far, because everything we've seen so far refers to essentially expert users doing a routine task. Right? So doing something that they've done hundreds of times before. And if you want to understand how long it takes people to start learning a system when they are not experts in it, then the natural GOMS language model enables you to do that. So it will let you also estimate things like learning times. But that's just an outlook on like where the variants of GOMS that exist out there. We're going to take a look at the simplest one right now, which is the keystroke level model. And we're going to do an actual example of how that works. All right, so KLM keying is tapping on a keyboard. Pointing is pointing to something on the screen. And again, it's an average, right, of all the possible distances and target sizes that you might have. Homing is an interesting one, the one that you may not think of, which is if you have a mouse and a keyboard, moving your hand from one to the other. Right? That actually takes also some time. Mentally preparing is one that refers to the time you need to, you can think of it in two ways. You can think of it as getting ready to do the next thing or verifying the thing that you just did. Either way, you know, some people think of it as the verification step of the last thing. Other people think of it as the preparation of the next one. Either way, people will pause for a moment when they do something. Like, for example, let's say you want to delete a paragraph, right? So you will select it, and then you will delete it, and then for a moment you will just check whether that was successful. And you can think of this as mentally preparing for the next step or verifying the last one. It doesn't really matter. And finally, there's also time when you are waiting as a user for the system to provide something, right? So to answer your input. So if you hit a button and the system takes some time to react, that time is also time that you spent at the task, right? Even though you're not doing anything. So these numbers are, that's not a lot of numbers, but I would recommend actually to try to memorize where these numbers are. If you don't remember them down to the last, tenth of a second, that's okay. But the orders are interesting because they tell you that, for example, when you build an interface that makes people, enter the name by having to move to the mouse, click on a field, and then enter the name, you've immediately, assuming they were at the keyboard before, you've immediately wasted basically 0.8 seconds because they need to do 2 homing actions, right? Plus another second for pointing. So that's roughly 2 seconds right there, just moving my hands away from the keyboard to the mouse to move the cursor to a new field and enter something. And I bet you that all of you have been at websites where you had to enter, like fill in a form, and every single field you had to click on with the mouse. That was because there was no tabbing to the next field, and you're like, ah! And the reason for that pain is exactly this, right? It's these 2 seconds for each of these single fields, on average, right, that are wasted of your time doing this. Compare this to how long it would take if you have the tab to move to the next field, right? Then we know it's 1 key press, 0.2 seconds. So I fill in my stuff, I hit tab, I get to the next one. And this is why it feels so nice and you feel so efficient and competent when you use something like this with the proper keyboard shortcuts and the system supports it. Because it actually is more efficient, right? And these are the numbers that are supporting what you've always felt subconsciously about this interface is kind of lame and this one is really, speedy and nice to use. All right, so this responding time, of course, has an influence on your actions, right? So if the system actually takes a long time to respond to what you did, you'll have this causality breakdown. You will remember this from Bloch's law and the experiments that we did, like watching these 2 balls collide. Remember the videos? So after 100 milliseconds, we have the problem that people no longer will consider the response of the system to be directly triggered by their action. It will feel like there's something going on in between, a little bit stuttering, and after about a quarter second, people are likely to try again, right? Because they think, oh, I guess I didn't hit that button right. So it's important to give feedback that the input was received and was also recognized. But that's just an aside. The key about the keystroke level model is really these times. And now we need to figure out how do we calculate this? Because I'm sure you're thinking, wait a minute, 1.35 seconds of mental preparation or verification time, I'm not doing that all the time, right? I'm not pressing a button if I enter my names like J, A, oh, what's next? N. Now that's not what I'm doing, right? I'm entering J-A-N, enter, and then maybe before hitting the enter key or after that, whatever, I'm going to check whether I mistyped anything, right? But I'm not stopping after every letter of something that I'm very comfortable typing that I type a lot. Like if you use a command line, like a Unix command line or something like this, you often type commands like ls or something. Right? You don't stop between the L and the S for listing your contents your directory contents. It's just one gesture that you do one after the other. So obviously, we're not always doing this mental preparation after every single gesture, right? So when do we do it? And that's where we're going to have a little bit of a weird way of finding out which M's to put into our sequence. The rest of the sequence is pretty clear, right? Keying, pointing, homing, and even responding, we can just determine by looking at how the system works. But the mental preparation, that's not something you can see or automatically derive. You need to have some guidance on where to put these mental preparation operators. And that's what the KLM gives you. So the way this works is you first list the gestures that are needed. So for example, assuming my hand is on the mouse and I need to type a letter, then it's going to be one homing movement to move to the keyboard and one keying operation to type a letter. That's obvious, right? HK. These are the physical gestures needed. Then you compute the mental preparation times, which is tricky, right? And this placement of these mental preparation times is described by a set of rules. And the way these rules work is that you have a bunch of rules. You apply one after the other. First, you throw lots of M's into your list, and then you remove certain ones again until you're left with the ones that should be there. We'll get to that in a second. Once you're done with it, let's say, for example, you determined for some reason that you have this sequence, like a homing and a mental preparation and a pointing and a keying action. Then you just add the times of each of these 4 operators, right? And you end up with a certain execution time. That's just an example. It's not derived from the one up there. It's just another example. And to explain the rules, I need to establish some terminology. So a string is, of course, a sequence of characters. A delimiter is a character that marks the beginning or end of a meaningful unit. Oftentimes, an enter key is something like that, or tab key, for example. Operators in our simple model here, in the keystroke level model, are just keying, pointing, and homing. The argument is the information that's being supplied to a command. So for example, if you say ls to list the contents of your current directory in Unix, that's no argument, right? It's just a command. But if you say ls docs, and docs is the subfolder that you want to see the directory listing of, then docs is the argument to that command. So here are the rules. You first throw lots of M's into your sequence. You put one in front of every key, just like I described, like J, N, etc. And you also place M's in front of all pointing gestures that select commands. What does that mean? A pointing that selects commands. I don't point to ls, when I'm typing, right? But when you, for example, have Photoshop open and you point to the line drawing tool, the line drawing tool is like a command, right? That's a command you give to the computer to select the line drawing tool. Or when you pick a menu from a drop-down menu. But not P's that select arguments for this command, meaning that if you have to, let's say, you have a function that's like the fill bucket, and you have to select the fill bucket, and then you have to select the option that you want to fill with the color. You would put the M in front of the fill bucket command selection, but not in front of the selection of the object that you're filling. Otherwise, the authors found it's overestimating the time that you spend mentally preparing and verifying what you did. Okay. So now we still have lots of M's in our stuff, right? Now we remove all the mental operations that are essentially anticipated, meaning you remove them between 2 other operators if the second operator is fully anticipated in the previous one. For example, if I am pointing to, let's say I'm on a system that has a menu bar, right? So I'm pointing to the menu bar and then clicking on the file menu. the point and click are essentially, for me, one continuous thing, right? I know I want to point and click to this. So while I do need still the mental operator in front of the P, if I'm selecting a command, I would remove the one that's in front of the clicking of the mouse button, because that is fully anticipated. Meaning that in practice, pointing to a menu and clicking on it is one continuous thing. So, this example here, point and click. If I'm selecting a menu, for example, or if I'm selecting an object, you would remove the mental operator between the point and the click. Next rule, we throw away more M's. Within what's called cognitive units, so contiguous sequences of type characters that form a name. And so the example I gave earlier, when I type ls or dir, right, to list my contents of my directory, I would still have mental operators in front of each letter. So, but the letter 2 and 3, I and R, are fully basically anticipated after I started typing dir. It's one continuous move. I don't stop and think while I'm typing it. So we only are left with the first M here, and the other two M's are gone, right? So MK, MK, MK turns into MKKK. So we have more rules to throw stuff away, right? Rule 3 says, if I have consecutive terminators, I can also throw this away. So if K is a redundant delimiter at the end of a cognitive unit, you delete the M in front of that as well. For example, if I type blah and then 2 returns, which would normally be at this point M and 3 keys, because I've already moved the M's between these keys, right? And then I would still have left MK, MK, for these 2 returns. I leave in the first one, but I remove the second one, right? This one goes away. This one doesn't, the second return doesn't get another thinking pause. Kind of logical, right? If you finish something with double return, you don't stop in front of each return character there. Next up, deletion of M's that are terminators of commands. So if a key is a delimiter that follows a constant string, then you delete the M in front of that. This is not for arguments or strings that change, but for commands that are always terminated with this key. So, for example, this thing here, if I type clear, or again, the dir command that I mentioned earlier, and I hit enter, then I'm going to actually remove the mental preparation in front of the final return. I still have a mental preparation at the beginning of the command. This one stays in, right? But at this point, I've reduced the number of mental operations down to just one mental prep, then the whole command, clear, enter, and that's it. Okay? By the way, this rule here often also comes up if you're typing programming languages, right? You type semicolon, enter, for example. That's also an example of 2 terminators where you wouldn't stop in between again. And the last rule is overlapping M's. If you have, and that's kind of obvious, let's say you're doing a bunch of things and now you have a mental preparation, but while you are mentally preparing to do the next thing, the system is also busy doing something. Those things can usually overlap. Right? So when they overlap, you don't need to count them twice. So meaning that if I'm waiting for a computer response, I don't need to assume that the person is just frozen there, not mentally preparing at all, but they're going to prepare for the next thing to do as they are waiting for the computer to wrap up their own thing. So I know this is a little weird and a little abstract, so we're going to go through an example now. Okay? Let's do this temperature converter. This is the task. This is Bob. Bob works in a biology lab, and Bob has an interesting job. Bob sits there at his desk, and occasionally other members of the lab shout at him and say, "Hey, Bob, how much is 43 degrees Celsius in Fahrenheit?" And then Bob goes in, types it in, and shouts back the answer. I know it's not probably a life-fulfilling job description, but let's go with it for a moment, okay? So he can use, he needs a tool to invert from Fahrenheit and Celsius to Celsius, or vice versa. He doesn't know which direction it goes. Actually, both kinds of requests are equally likely. He can use a keyboard or the mouse to enter the temperature. That's open. And we're making a bunch of assumptions. And by the way, slowly get ready. You're going to be asked to do something here in a minute. We're assuming that the window that is awaiting the input is active, right? So he doesn't need to switch from, playing Minecraft or whatever to the temperature converter. That's already the front window. Let's also assume an average of 4 typed characters, including the decimal point and the minus sign. So on average, 4 typed characters. Sometimes it's 32.7, that's 4 characters. Sometimes it's minus 6.8, that's also 4 characters. Sometimes it's minus 32.7, that's 5 characters, but then other times you have less than 4. So on average, we're going to say, to simplify things, 4 characters for now, right? We're also going to assume for the moment no typing errors. Bob is very proficient with his, keyboard, so he's really fast and doesn't make mistakes. These are all assumptions that are making things a little unrealistic maybe, but not too bad. And once we have an idea for this ideal scenario, then we can think about, what does that mean if he does make mistakes, right? So here's the task. I want you guys to get together, groups of 2, for example, and design an interface for this. You only need to design one interface. You can make up your own. Make it any way you want for your task. A naive interface could look like this. You say, well, I got to select the conversion direction, right? Fahrenheit to Celsius, and I got to select, and I got to enter the number, right? So we might say, okay, here's an interface with 2 radio buttons. Only one of them can be selected at any time. I need to select the conversion direction first, right? And then I have to enter the numbers. And when I hit enter, after entering the numbers, I get the conversion being computed, right? Not completely. Anybody have an interface like this? Oh, okay, you're all, similar. Okay, we're going to see how fast this is, right? I'm going to show you a way to calculate how fast this is. This has 2 cases, right? Either I need to actually click on the radio button to change the conversion direction, or the right direction is already selected, right? We said each cases are both likely, so each of them 50% chance. So let's do the complicated one first, because the other one is then just going to drop out of that too. So let's assume we need to actually do the conversion direction. So I move my hand to the mouse, because we said the hands are at the keyboard, right? That's where the starting point was, at the keyboard. So if there's a mouse action, we need to do homing. We then need to use the mouse to point to the other button, right? Because we need to do a selection, we said, in this case. And we click on that button. So that's a homing action, a pointing action, and a clicking action. Next, we need to move from the mouse back to the keyboard and type the 4 characters, because we said that's the average length of the command, of the number we enter. And we have to finish it up with hitting enter. So that's the homing action again, 4 keys plus the enter key. So that's the pure physical sequence. Now M's, right? We throw M's into lots of things here, as we can see, right? So in front of all of these separate actions. And then we start deleting them. Right? We remove the anticipated ones, meaning that we drop the ones, for example, in front of this key, because we said point and click at a location, like clicking on a radio button, for example, we always drop that M. So that's why this one disappears. Next, we delete the M's inside what we call the cognitive unit. And in this case, the cognitive unit was the number, right? So we don't stop after each digit. We know it's 32.7. So we only stop at the end of that. So that's why we drop the M's in front of the second, third, and fourth character entered. Not the one before the first character, right? That is still there. So the result of that is this sequence, right? HMPK, HM4Ks, and MK. There are no double ends or anything like that. So with this, we are basically done with applying the rules. The other rules, we don't reduce this any further. So what we see here is, what's modeled here now is that we have 3 moments where we could say stop and think, right? One is to select the direction, right? To click on a target. That's a cognitive thing that requires preparation. Then actually entering the number and then verifying if the number is correct. The estimated time here, you can calculate that as 7.15 seconds. The other case is that we don't need to do the pointing, right? In this case, of course, we can drop the whole homing to the mouse, changing this and clicking and homing back. That is dropped. So we just end up with the M, the 4Ks, and the MK. That's 3.7. The average then is of these two numbers is 5.4 seconds. According to this model, we would be at a bit over 5 seconds for doing a typical conversion. Okay. Yeah, couple comments. Go ahead.
Why we didn't count reaction time to see if the...
Yeah, so we don't count reaction time because, or response time. You mean the R, right? Response time. Response time is really only if the computer needs significant time to do anything. And I'm assuming that this conversion takes no time at all for the computer, right? There's no waiting time on the order of even a millisecond or so before the result is displayed. So we don't need that. Yeah.
Is it only interesting to see if we use it for the first time? Because if there comes another number at the interface, we have to do steps like deleting or going back to the enter field.
Excellent point. Yes. So right now, you're asking about what about repetitive use, right? If something has already been entered and I'm using it again. This will come up later when we look at optimizations for this. In this case, you can make the assumption that you say, well, the moment I selected one of these numbers, or when the display, when you press the enter key, the result is being displayed, and typically what you would do then is that you select that text as well. So the next time I get into that text field, I can basically delete things, right? So when somebody clicks the radio button, for sure I know a new conversion is coming up, so then I can just clean the text field out. Although, now that I come to think of it, if I don't click the text field button, we might need something extra to make sure that the text field is empty, even in this case. Yeah. That's something I need to think about. Yeah, go ahead. Yeah, so what are you doing to deal with that?
It's a big field, and when you type in the first row, after enter, it goes down, and then you are up to there in the first row to type the next. It's already set to. You don't have to use the mouse.
Okay. And even if I need to change the conversion direction?
We have to enter to type in F or C. You don't have to.
Yeah, good. So those are all improvements over what we're doing here that will speed this up. So we're going to get much faster than this for sure. All right, so we're going to look at more examples of improving this later on. But do you want to throw a couple of numbers in here, like who can do faster than 5? Okay, quite a lot. Anybody got something where they think it's faster than 4? Okay. Anybody thinking they can go faster than 3? Okay. Faster than 2? No, faster 2 would be weird, right? Because we need to at least enter, we need to do something here, right? But, okay, so we're going to take a look at a couple improvements, and what I would suggest is, take a look at those improvements, see whether they map to your own changes that you made, or whether you have yet other ones. So, yeah, no,
I've got a question about the last page.
yeah.
I think one of the deletion rules was that when we enter something, like for example clear, and we hit enter,
Yeah.
that is one.
Yes.
One input sequence.
Yes.
Couldn't we remove the M before the last K, or is that?
Excellent question. No, we can't. If you enter something like clear or dir or ls enter, that is a command that you've probably entered 100 times. So it's a cognitive unit as a command. So it's a delimiter of a command. And the delimiter gets basically merged with the command in your mind, because that's just the command as a whole. But when you enter an actual number, you do stop before the delimiter, because the number is going to be different every time. So it doesn't merge into that same sort of fluid one sequence thing. Does that make sense?
Yeah.
I think that's there. It's also modeled in the rules that way. Did you have a question?
No.
No? Okay. Right there.
If we didn't have the conversion buttons and like having the tags on above the input fields and just having double direction like Google, when you Google some conversion and put in the direction. Was entering the input field also, does it need N? Or?
I'm not sure I know what you mean.
At the beginning,
Yeah. So at the beginning, what you do know is that the window with the temperature conversion is the active window. You can make one text field inside your system being active, but it would have to be sort of the one, each time it has to be the same one, right? Or at least it has to be the one that was last used. You can't assume that it magically knows what's coming next. Right?
But for entering it, for example, I just do one homing to the mouse and then decide to enter one of those fields. For example, if it is C to F,
Okay. Yeah.
It does have a network.
Yeah, that's similar to what you were asking, I think. Yes, because that's still, selecting the direction would still be a separate mental operation from entering the number. Yeah.
But selecting an input field by default in a text field form.
It can be pre-selected. Like one of them can be pre-selected, but it has to be. You can only assume that it's the right one 50% of the time. That's kind of the idea.
Whenever we decide to select an input field, we need that N.
Yes. Yeah, I think I know what you mean. Yeah. So the selection of the input field is a separate mental operation from entering the number. Yeah. All right. So what we're getting out of GOMS is a couple things, right? So first of all, we get execution times out of it. We saw now we could take an interface. I didn't have to build it. I could do the calculation purely based on knowing how it works. But we have to remember that it's only execution times with the natural GOMS language, also learning times. But for most of the GOMS models, it's only for trained routine users of repetitive tasks. So this gives you a good estimate of how much time people are going to be using to do the task once they have been trained. If you do go to the natural GOMS language model and you also have beginners in there and learning times and so on, then you can also estimate training costs. But the most basic thing of GOMS is the daily use. You can also, certain versions of GOMS also let you reason about errors and how likely it is that people make errors, but we're not going to touch that. The nice thing about this is that we can link this to other costs, like, for example, the cost of buying a new system, the cost of changing a system, updating it, and so that gives you answers that are expressed in money units. What works nicely with GOMS is if you have two alternatives for an interface and you want to decide which one is the better one, like we're going to do with the temperature converter. The absolute numbers of GOMS may be off, like for example because of the reasons that I explained for the CPM model that says people are actually a little faster overlapping certain things, but the relative comparison of different interfaces tends to stay the same, right? The ranking. So there there's a nice example from Gray that said that I think this was a New York phone company, 9X, and they had a, this was in the 90s, they had a system that was basically, command line based. It was text based, a text based system in the phone exchange. So where people were, handling complex aspects of the phone system to keep it running. Not, talking about operators, not, the end user at the phone. And so the 9X was proposed by a company. They got a proposition of introducing a new system that had a cool graphical user interface. This is the early 90s, so people were like, yay, mouse and colorful screens and so on. Somebody, thankfully, went in and did a GOMS analysis of the two systems. And they found for those highly trained operators that don't do anything else, for 8 hours a day than operating these systems, the graphical user interface system would actually have been slower than the existing text-based one. So the text-based one wasn't as sexy, was kind of boring and looked old school, but it was actually the more effective one. So this is an interesting finding, that said if the new computers would have gotten introduced at that phone company, it would have cost the company $2 million a year extra just in wasted operating times. So this system lets you estimate the effects of a redesign like this, because what you can do is you can say, all right, if I change to this new system, and let's assume it's actually better, right? Let's assume we actually improve it. Then I have a long-term saving that I can express as cost, but I also have the cost of changing, right? I need to train everybody to use the new system, and they will be less effective while they're learning it, et cetera, et cetera. So now you can start thinking of, is it worth, introducing this new system that's going to be a little bit more effective when it costs so much to retrain everybody? So that's a useful thing to do with GOMS as well. Another thing that GOMS is good at is to use it as starting point for documentation. Because think about it for a moment. When we saw the instructions, you remember the task like highlight arbitrary text, click on the beginning, then shift click on the end. That was basically like a manual, right? How to do it, like really broken down to the elementary operations. So a good GOMS model is actually an interesting source also for documenting how to do things in the system. But there are a couple areas in which it doesn't work so well. So I'm going to give you one situation. We build interactive exhibits sometimes. Like we've built interactive exhibits for museums in Vienna, and we've built them for like the World Expo in Shanghai and all this kind of crazy stuff. So people come to these exhibits while the exhibition is running, or they're a museum visitor, and they interact with the exhibit and they do something with it. Could I use a GOMS model in this case to find out whether my design is good or which alternative design would be better? Yeah?
Definitely no, because it's not I would say it's not a really routine thing.
Right. Unless you are a museum nerd and you go to the same museum every day, you're not going to become a routine user of this exhibit, right? So this is a situation where you have typically a one-time, first-time user, so you can't use a GOMS model in this way to understand whether one design is better than the other. Other factors are more important, right? For example, to easily understand the system and easily use it without any prior knowledge, those are going to be much more important. Yeah.
Could you use the variants of the GOMS system for like non-routine users where you have a lot more M's, so a lot more mental preparing for what task to do because they're thinking about everything, or?
No, the M's don't work that way, because the way that we insert the M's and then remove them again is...
Without removing it.
Yeah. But the fact that we are removing them is basically because of how the brain works on a fairly fundamental level. So you can't just leave all the M's in and say, like, beginners are going to pause for 1.35 seconds between every letter. It's not that simple. And the more important thing is, I think, GOMS is for routine tasks that also need to happen oftentimes, right? So it only pays off to even do this analysis if it's a task that's being done repetitively. So if I do it only once in my life, why have a GOMS analysis? It doesn't really pay off. All right. So don't use it for casual users, or if you have a completely new UI technique. So the first time somebody came around with a voice-based interface, I wouldn't know how to apply GOMS. Before I can apply GOMS to this, I need to determine the operator times. The operator times are like a basic vocabulary I need to understand and know about and have estimates for. If I don't have those numbers, I can't use GOMS, right? So as new interaction techniques were developed, for example, gesture-based interfaces or so, or even for mobile phone touchscreens, people did research and tried to determine good numbers for typical actions on these new devices or in these new interaction modalities so that you could use GOMS with them. If we want to understand more about information efficiency and how to measure it, we need to take a bit of a look at information theory. The goal here is that I would like to give you a way to essentially compute how fast an interface can be theoretically, like what is the minimum amount of interactions necessary to do a task with like the optimal interface that we don't know what it looks like yet, but it might exist, and we have like the minimum amount of, for example, keystrokes necessary to do a task. We can determine that number as the ideal sort of goal, and then we can look at actual designs, see how many character actions or how many clicks I actually need to do a task with that interface, and then I can take these two things and put them into relation and say this interface is 80% effective, right? It's 80% of the optimum, and maybe that's the interface to go with because it's very easy to explain and very easy to explore and understand the first time you see it. Maybe you don't want to always have 100% efficiency. Maybe you can't even come up with the interface that does that, or maybe it's so weird that nobody will understand it. But we're going to try to find these numbers. So as you know, you can quantify information as the amount of data conveyed through a communications channel, right? You've learned that in information theory. And communication channels can be speech or messages that are being sent upon a click. In our case, we're going to take a very, very simple look at that, and we're going to essentially look at simple things like displaying digits or entering things as characters on a keyboard or selecting things with the mouse. And what we're going to try to find is the lower bound of the amount of information that is required for a task, because that lower bound is independent of an interface design. I'm just looking at the task itself, not thinking about how the interface is going to look that does it, but the task itself should be able to tell me what the minimum amount of information is that I need to convey to do it. And if I have this number, then I can talk about efficiency of an interface, because this ideal number of the minimal amount of information required for the task, let's say it's, I don't know, 10 bits, divided by how much information the user is actually supplying in a concrete interface, let's say 20 bits, then gives me the efficiency of the interface from an information theoretic point of view, in this case 50%. Right? So I'm saying to really enter the data that really needs to make it across the line for the temperature conversion is this much in bits, and this is the stuff that people are actually doing to get the information across, and that's so many bits. It cannot be less than the minimum, because that information needs to make it across the line, but it can be more. And then we have some kind of unnecessary interaction happening that makes it less than 100% efficient. Although that might be fine, right? Like I said, because maybe it's that way it's very easy to understand or has other convenience functions. So this E is between 0 and 1, right? 1 would be ideal, right, this efficiency. 0 is when you basically, the task doesn't require any information, right? So that thing up there is 0. Then anything that the system makes you do is unnecessary, right? There was for a long time a dialog that would pop up when you started Word on the Mac and you would search for something. And when it wouldn't find something, it would pop up a dialog that said, Word has finished searching the document. And you had to press OK. And I am actually providing some information to the system here by pressing OK. I'm confirming this dialog, making it go away. I'm doing some action. So there's some information flowing from me to the system. But the system isn't, the task itself doesn't require any information. It's done searching the document. There's no action required from me to tell the system something, right? Other than removing this dialog. But that dialog could also have been just, a message somewhere on the border of the system that just stands there, and I can just continue my work. I don't need to confirm this dialog. But, at that time, Word was very, well known for asking for these, like, oh, look at me, I can show you a dialog, and now you need to click it away before you can continue your work. To make this more tractable for us, we're going to look at not this theoretical efficiency, but we're going to look at character efficiency. So if we do have an interface that we can break down to essentially character interactions and characters being displayed and characters being sent across this communication channel, then we can work with the minimal number of characters required for the task divided by the number of characters that are actually being entered in the UI, right? So if you have a very simple text-based UI, essentially, then this works fine. So, how do we measure this information that's needed? Well, information is measured in bits. We know that. 1 bit means a choice between 2 alternatives. Everybody knows this because it's, we know this from computer science. But if we have n equally likely alternatives, note the word equally likely, then it's very simple. In general, we say the total information amount is log 2 of n. Simple enough, right? And each of these alternatives that I'm entering only has 1 divided by n of this information amount. That's also pretty clear, I think. Now, if I have n alternatives with different probabilities, so not everything is equally likely, then I need to do a tiny bit more math, because if I have a probability p of I for a certain alternative, for example, if it's less likely that negative numbers are being entered in my temperature converter than positive ones, something like this, or if you have a text and it's much less likely to enter the X key than the E key, for example, then each alternative has a likelihood p of has an information content of its probability, its likelihood, times that information log 2 of 1 divided by pi. That's just a more general formulation of what we have down here, right? If you insert all of these are equal, all probability is equal, then you have 1 divided by n, and we're back at this formula. Sure. And this means then finally that if you want, in this case, to understand the total amount of this, you just sum up all this, right? So you sum it up over all of these i's, and then you get the information content of the total information amount for cases where the likelihoods are not all the same. So when you look at the situation as a whole, what this means is that we are now basically, we assume that we know the probability of certain messages coming up. And what we can do with this is that we can determine the total amount of information as in bits that goes across the line, right, from the user to the system in this case. If you want to understand an intuition about this, then I found it quite helpful to think of this amount as freedom of choice, right? The more freedom of choice I have to choose one or the other thing, the more information content is basically in the system. If there is only very few alternatives, then the information content is pretty low. Right? If there's lots of different alternatives, the information content is higher, right? Because it can choose from different alternatives. That's why displaying just a 0 or 1, like if there's just a lamp on or off or something, that only communicates 1 bit, but if I can enter a digit, then I have 10 different options. We actually talked about this earlier in DIS1. So, what about our temperature converter? We had a couple, we can make a couple assumptions. We already talked about that. We said we wanted each conversion direction to be equally likely, right? Now, to get a little more precise, we're going to make a couple more assumptions. We're going to assume that we have mostly positive measurements and some negative ones. 3/4 are positive, 1/4 is negative. We only have decimal input, so we always have a decimal point. That's what we're saying, right? We never have 25. Right? There's always going to be a decimal point. All digits, 0 to 9, we assume to be equally likely. That's maybe not 100% realistic, but let's go with that for now, not to make it too complicated. And we're continuing to assume that we only always input 4 characters. So that means if we make these assumptions, that makes this task actually able to for us to model it statistically and determine what the character efficiency of different designs of our temperature converter is. Because we now basically have our input patterns as basically 25% are negative, right? So that means they start with a minus sign, and then since they all need to have a decimal point, there can only be -.dd, minus dot and two digits, or minus 1 digit decimal point and another digit, right? So that's the 2 options there, and the other half, the 75% that are positive, basically means that we have a likelihood of 0 to 9 for each of the 3 digits that are being entered, right? Because all the positive patterns need to have 3 digits and a decimal point. Otherwise, we don't end up with 4 characters of input. And if you take, for example, the negative numbers, like minus 5.7 or something like this, you have 2 digits in there. How many different versions of that are there? Well, there's 10 options for the first digit times 10 options for the second digit, right? So there's only going to be 100 different values that have the format minus d point d. Whereas in the positive case where you have 3 digits, you have, of course, 1,000 different options for all the digits there. This will become important when we add up all the likelihoods. Now let's look at a couple of efficiencies here for our temperature converters. Here's a slightly improved version that says to convert temperatures, indicate the desired scale by typing C for Celsius or F for Fahrenheit. Then type the numeric temperature, then press the Enter key. The converted temperature value will be displayed. Okay? So that's maybe an alternative that is already faster than our very clunky use the mouse to change the selection. So basically I type C or F, then the value, then Enter. Okay? I've now removed the mouse from the equation. That means I have this sequence, the M in front of the first key. Then I have my 1, 2, 3, 4 keys of the value, and then I have the mental preparation for the Enter. Okay? This would take 3.9 seconds. You can do the math, but this is basically what comes out of this. And the efficiency of that, I'll show you how exactly I get to the efficiency in just a second. But it should be clear what I really, really need to communicate is even less, right? Because what I really need to communicate is basically just those 4 digits that I enter and the selection whether it's Celsius or Fahrenheit, right? That's all that needs to go in there. Now let's look at a second design. Here, I remove the final enter by saying, now wait, I can do it this way. I can let you enter a value here, always in the left-hand side. And then you enter C or F to decide which kind of conversion you need, right? So I've now removed an enter key from this. So that brings it down to M and just 4 keys, and then MK.
What for is the last MK? If we remove the enter, why is there still an MK at the end?
Because the C is coming after the numbers. So I basically say 25.7 C. I don't have the C in front of it, I have it after it. So the first M is for entering the number, and the second M is for choosing C or F to start the conversion.
For example, we didn't have another M just for the C or F. We had the number and everything together.
Yeah, that's correct. But in this case, the C or F that you enter is also your triggering the conversion. So that's the mental preparation or verification that you do as you basically wrap up the operation. So at this point, you're at 80%, bringing it down to 3.7 seconds. And here's yet another design that is called a bifurcated design, that basically, similar to some of the ideas that you guys have mentioned, you type in the number to be converted on the left. You don't type C or F, and it does both conversions at the same time, right? So when you do that, you just enter your 4 digits here, your 4 characters, sorry. They're not all digits. Some of them are the decimal point or a minus sign. And then as you do that, the numbers appear here, right? So there's no enter, no C, no F. So I'm just entering for the 4 characters that I need to enter. I have one mental preparation because that's always there when you enter these kinds of sequences. And that brings it down to 2.15 seconds, or a character efficiency of 100%. So what fascinates me about this, I didn't come up with these designs, by the way, right? I didn't make these up. These are from a book by Jeff Raskin, who was one of the designers of the original Macintosh, and then went on and wrote a book called The Humane Interface. Really interesting book. I met this guy when I was at Stanford. He gave a talk there, and was quite an inspiring person. And so what I like about this method is that I can now say, this interface, from a mathematical point of view, I can prove that it is as fast as you can get. Right? This is the information theoretic efficiency. Now, remember, we're not looking at questions of how easy is it to enter these things. Maybe I designed a system that's information theoretically really efficient, but it requires, I don't know, using an input device or something that is very complicated or takes a long time. Those are all other things. Or maybe the interface isn't good from an aesthetic point of view, or it's confusing. There's all kinds of things that could be going on. But from an information theoretic point of view, I know that if I design it this way, it's going to be as fast as it gets. Nobody will be able to make an interface that information theoretically is more efficient than this, because we're at 100%. Yeah?
So the last example, the user has to confirm whether he needs the Celsius or Fahrenheit after they already input the number.
He actually doesn't. Right? The system always does both conversions.
The system does both, but he
Yeah.
needs to prepare in his mind what number does he want. So
Yeah.
we don't evaluate mental stress or mental exercises he needs to do. So
No, this kind of modeling doesn't give you the tool to estimate that. But you're absolutely right. If I were to try this out, you would probably actually still have to run some kind of study or make some kind of observation to see how well people get along with this. This is what I meant by saying, yeah, this is, that's not the only truth about like what's the best interface. Yeah.
So we could trick this whole procedure by just providing a very large lookup table with all numbers that would be possible.
Yeah.
Then we would have 0 input keys. And
Well,
have
yeah.
perfect efficiency.
Yeah.
And say that the user needs to perfectly find the column he needs on the first try.
We actually talked about this. You said the same thing. It's like, why don't I just put a big old table on the wall and let people look it up? Yes, in that point you have no more interaction going on, right? You're not inputting anything. You're just looking things up. But it doesn't work with this model, but there is Hicks' law, for example, that tells you that as you let people choose something from a larger and larger list of options, which I would probably say is similar to what you're describing as a lookup table, the lookup time grows, of course, with the number of options, and it grows logarithmically. It's actually quite similar to Fitts' law, but this is, for example, what people have found when you give folks menus that get longer and longer with more and more options. They found that that doesn't come for free. It does cost something. It doesn't cost linearly, but it costs roughly logarithmically the longer the menu gets. Until the menu goes off the screen and you need to do weird things to look at things that aren't even visible yet. But you're right. At that point, you're leaving the bounds of what this model can tell you, and that's what I meant by saying there are other factors that will influence how effective and how useful an interface is in reality, right? It can only look at this particular facet or give you this lens onto the interaction. But I think it's still fascinating because many times we don't get anywhere near this 100%. And being able to at least reason through and giving you the option to think, is there a way to get closer to this? Or why does this interface feel more snappy? Why does it feel like I need to do less unnecessary stuff? Is there a way to optimize this? This gives us, I think, a good tool, right? But it's like with so many things in interface design, right? You get lots of tools, you get lots of lenses to look at a problem, but none of them is just, automates the design to a perfect solution, unfortunately. Yeah. Yeah, but that's a really good point. Yeah, go ahead.
I didn't understand how the system understands which Celsius or Fahrenheit is.
You mean in the last one, the bifurc? Yeah, so it doesn't. It basically just takes the number you enter and interprets it once at Kelvin, as Fahrenheit, and converts it to Celsius at the top. And then it looks at it and thinks it's Celsius and turns it into Fahrenheit at the bottom. And you then look at the row that you're interested in. So if you say, I have a value in Fahrenheit, I need to convert it to Celsius, you type in the number and you look at the one that says Celsius. That's how it works. And that's why you made that comment saying, like, yeah, we're kind of offloading now the burden to the user to now pick the right result row, right? That's why this could feel like cheating. But I think the benefit here is that this thought process leads you to new interface alternatives that you probably wouldn't have thought about. And then you need to figure out, is it actually a good idea, right? But so much about interface design is about even getting the ideas in the first place, not so much about finding the best one is actually, we have techniques for that, but finding the alternatives to test is the one that we have very few techniques for. That's why I think this is interesting. Yeah?
But if you look at, like, we want to do it more often than just one time, like
Yes.
design, the last option becomes worse than the second option, I think.
Yeah, repetitive use is a whole different beast. You're absolutely right. For example, and you brought this up before, right? Yeah. What if I use this already and there's some number in there now, and now I want to use it again? What am I going to do? So you could say if you use this interface here, where you type C and a number and then enter, the system could use the enter key and could actually then put the result in the text field. It could also highlight your entry field here, like select all the text, so that the next time you come back to it, a second later or 5 minutes later, the moment you start typing, the old value disappears. Pretty easy. So for repetitive use, this is easy here. Not clear how that works here, right? That's another catch. Because if I type something in here, there is no delimiter. So in fact, this system will have to start converting as soon as I enter a digit. When I say 1 here, it will have to convert the 1 into Celsius and Fahrenheit. If I add a 7 behind that, it will now have to take the 17 and convert that, etc., etc. So removing this here to use it again isn't obvious, but you seem to be having some ideas. So what do you think?
No, I mean, I was just gonna argue like basically the same direction with you, but like with another argument that it's like I wouldn't say that it's only cost like the computer time, it also costs like, or at least I could imagine that the user would be kind of distracted. Whereas the other one, they could focus on strictly just typing the number in, whereas they would like be distracted by the number constantly changing and appearing and disappearing.
Possibly. Or maybe they love it because it makes it so super fast, right? They don't have to hit that extra key and they just type in the number. It might be more like, I don't know, like a real world physical thing when as you put things on a scale, then, with each weight you put on scale, the, result changes. That will require testing, yeah.
I just want to make a quick comment on how you could maybe get this to work repetitively as well.
I knew this was coming, so let's hear it.
Because we defined that we always have 4 characters, so we could automatically highlight after we entered 4 characters.
Right.
Which is not perfect, but it would.
Yeah. So that I need to that was not what I was expecting. So thank you. You managed to surprise me here. But so the idea of the 4 characters was purely for analytical reasons, right? We said we want to estimate whether this is optimal or not, and for this we're making some assumptions. So this is only 100% character efficient if we make the assumptions we made up there. And that led us to an interface that is pretty darn good, probably in practice too. Maybe not 100%, but I wouldn't go and make that analytical assumption into a rule for how you can use it, because then this becomes an interface that only works with 4-digit numbers, and that's not the intention, right? So the intention of the 4-digit limitation or 4-character limitation was just for analysis, not as a design for the tool. I was expecting a different thing, because at this point somebody says, but we could make it go away after a time, right? So, and that's actually often what you get, right? With when you don't want to hit OK for a dialogue, oftentimes systems blend it in and they make it go away. The messages on your smartphones, right? They appear and then there's one setting where they go away after a time. And that sounds like a solution for this one, but comes with a whole new can of worms. Because something that goes away after a certain time, maybe I needed to still write down that number and I wasn't done yet because I was distracted for a second, right? So then it went away too fast. Or maybe I need to type in one number and then I immediately need to type in the next one, but it hasn't disappeared yet, so then it's too slow. So what you did at that point is you put a timeout in the interface, and as we'll learn next time, timeouts are evil. Like timeouts are always evil. It's a very simple rule to remember, because they never hit the right time. They're always too long or too short to be actually practical. And yet developers all around the world keep coming back to the timeout to solve problems because, frankly, they're too lazy to come up with a better solution. Who's had the Deutsche Bahn website timeout on them after you looked up that perfect connection and you were just about to enter that credit card and you had to look it up and find it in the other room and then boom, your session has expired. Please find that again. So it's the devil incarnate. That's what timeouts are. But I can get on a soapbox for hours to talk about timeouts. So let's not do that. Let me just wrap up with the temperature converter here. So the input assumptions here, why we get to these 67 and 80% character efficiencies, was simply to say that we assumed from the previous slide that we have basically 4 characters of input, right? And if we have 4 characters of input, then this is as fast as you can get, right? With only 4 characters being actually typed. If you wanted to get more detailed, you can look at it from this perspective with different likelihoods, right? So we said we always have 4 characters. These are the different ways this can come out. That could be -.dd, -d.d, -.3ds, or d.dd, or dd.d. These are all the options that you have for 4-character input. How likely are these? Well, we know the negative ones are 25%, so those are equally likely.
And we know the positive ones are 75%. So these we can assume also to be all equally likely, right? With me so far? All right. How many different options do we have? I said that 2 digits means there's 100 different values for this format. Same here. These each have 1,000 different values because there's 3 digits in it. Also easy. How likely is each of these? Well, that's exactly that probability here, right? 12.5% versus 25%. So that's the likelihood of seeing these, every single one of these, right? So 12.5% divided by 100 values gives you 0.125%. Still clear, right? Easy enough. What's the information content in bits for each of these? Well, since we can compute the information content of a single alternative with this formula, pi times log 1 divided by pi, we get these values. So you can already see that because we have more different values here, each single value has a little bit less information per bit. Right? Whereas here, we have only 100 divvying this up, so it has a little bit more information for each single alternative. But, of course, there are only 100 of these, so overall, this only has 1.2 bits of information in it. Whereas these, since there are 1,000 of them, they each, if you add them all together, have 3 bits of information in them. A little hazy maybe, but still mostly with me, hopefully. So what that means is this tells you the minimal info required for the task, because that is simply adding up these numbers, right? At this point, then I know, okay, so overall, I get to 11.4 bits per message. That's the information content of each entered format, because as it divides itself statistically over these different formats, and I know for each of these formats what its information content is, if it is chosen, then I have ultimately this total number of content. This was a very convoluted way of arriving at this number, but what we got out of this is that we actually got a lower estimate. You could also have said, it's, I know we have 10 digits and a minus sign and a decimal point, right? And I have 4 digits. So you could simply say 4 digits, each with 12 different positions. So that's 4 times log 12, and that gives you roughly 14 bits. That's a good estimate, but it's not as good as this one. So you can see, if you analyze the message more closely and look more closely, what can actually be at each position. Like the minus sign can never be at the last digit, for example, right? So there are less possibilities. So because there are less options to choose from, remember what I said earlier about likelihoods, because there's less freedom to choose, the actual information content goes down on this thing, right? So the minimal information content for the message is actually at 11.4 bits per message. And what that then means is, now I know, as I enter, if I look at different keyboards I could use with the temperature converter, because we haven't talked yet about what kind of keyboard Bob is using, right? Let's assume he's got a full-scale keyboard like this in front of him. Then the information efficiency of this setup with this keyboard is going to be 11.4 bits divided by the information supplied by the user. If you have a 128 key standard keyboard, which is roughly, technically you would say, well, that's got to be 7 bits per key, right? Because 128 keys. But it actually isn't, because in fact, the usage, the likelihood to use certain keys is vastly different between keys, which brings down the information content again. Right? Just like with the temperature converter 4-digit format, if the likelihoods aren't equally spaced, then information content goes down. So we end up, in practice, this is a number that I'm not going to derive here, we end up with roughly 5 bits per key. And that gives you an efficiency of 11.4 divided by 4 times 5, because you press 4 keys, each with 5 bits, of roughly 55%. So what that means in practice is letting Bob do the temperature conversion task with a 128 key full-size PC keyboard is pretty inefficient from a device point of view. If, on the other hand, you gave him just a numeric keypad, so just the stuff up here, which has 16 keys, it's much more effective. You are at 70% effectiveness. And if you gave him a dedicated keypad that only had the 10 digits and the minus sign and the decimal point, and you removed everything else, you would have created, from this point of view, the perfect input device for the task. Because there are no keys on there that you don't need. Right? So every key matters, and it brings up then the information efficiency to 80%. Not 100% because they're not all equally likely to be used, but you would be at roughly 80%. All right. Yes?
Could you improve the input device efficiency even more if you have the minus sign disappear and switch for the decimal point if you don't start with it?
I guess you could. Yeah. And that would become an increasingly confusing interface, but you would probably push up the efficiency further. Lovely. Yeah, the disappearing minus sign. I hadn't thought of that. All right. With that bizarre thought, let's wrap it up for today. Thanks, everybody, for listening. And we're going to continue next week with the 10 golden rules of interface design, one of which is going to be about timeouts. Thank you.
This content was provided by RWTH Aachen University.